So what we'll be talking about is granular media filtration. In this segment, we'll look at the design of a rapid sand filter, focusing on the calculation of the hydraulics of the clean filter bed and the hydraulics during backwash. What I'd like to do now is we're going to go through an example. This will take the rest of today and on Friday. What I'm hoping to do is we'll get through the head loss calculations for a clean filter bed. So the question is, are the wash troughs serving the purpose of increasing the backwashing efficiency? The wash troughs are really capturing the water. So you need, as you're backwashing that filter, you need to be able to capture that water. And the wash troughs are basically your collection device. So we have a situation. Okay. We're installing rapid sand filters. Good. Sedimentation and then filtration. In this case, you're told that you have a design loading rate of 200 meters cubed per minute. Decreases size. Okay, that's good. We have a design flow rate of 0.5 cubic meters per second. You're told that the maximum surface area of the filters is to be 100 square meters, but the desired area is 50. And what we initially are looking to do is to calculate the clean filter bed head loss and determine if it's reasonable. We want that head loss less than 0.6 meters. We'll use the following assumptions. We have provided some data on the sand. We're told that the specific gravity of the sand is 2.65. We have a shape factor of 0.82. The bed porosity is 0.45. We're designing this for a temperature of 10 degrees C, and the depth of our sand is 0.5 meters. This information here would be provided from the manufacturer. So what we have is we have the sieve size designation, we have the size of the opening, and we have a cumulative mass passing. Now, the GLUM standards state that the recommended maximum filtration rates, that's V sub A, is 360 meters per day for dual media filter and 180 for a single media. The problem states 0.5 meters of sand, so we're going to assume we have a single media. So even though you're told here that your design loading rate is 200, we're going to make the decision as the engineer that we really want to reduce that to 180 to comply with the GLUM standards. This is an iterative process, and you'll need to think about it as such. And my advice is to set up an Excel spreadsheet to allow you to iterate on a solution without having to go through multiple calculations by hand multiple times. And you'll definitely need to do this for the design project. So my advice is do it for the filtration homework, and then you have that same Excel spreadsheet for your design project. So let's just start. Okay. And we're going to start with got this equation here for the surface area. And we're going to pretend we didn't look at that initially. You just followed what the design engineer or what the specification said. So let's just initially look at that using the 200 meters cubed per day per meter squared, or meters per day. And that would give us 216. In this case, the number of filters is equal to 216 meters squared. Said the preferred filters that are 50 square meters, and that gives me 4.32 filters. I can't have 4.32 filters. So what do? What are my options? I can increase the size, or I can increase the number. Increasing the number of filters means that you're increasing increasing the complexity of your plumbing system. Okay. So we've got to round up or round down. Okay. We're already at the maximum, so round down would be a problem. So we can look at using 6. So let's look at using 6. If we use 6 filters and we keep our filter size at 50 square meters, and we have 6, that gives me an approach velocity of 144 meters per day. That checks. What if I have one filter out of service? So now I only have 5 in service. That's 172 meters cubed per meter squared per day, which also checks out. So I can use 6 filters at 50 square meters. I'm perfectly fine. In terms of that approach velocity, it's less than that 180. That's less than 180. This is also less than 180, so we're good. Now, we could also try, can we achieve a approach velocity of less than 180 with only 4 filters? And I have 4 filters, but I increased the size to 80 square meters. That corresponds to an approach velocity of 135 meters per day. And then with 1 filter out of service, I would have an approach velocity of 180 meters per day. So either situation is acceptable, and it most likely would come down to cost. Cost and space availability. If we increase the number of filters, that's more space. It's also more valving. It's more monitoring that we need to do, so it's more monitors that we have. So there's a cost associated with that. The next thing we want to do is to calculate the head loss of the clean filter bed. So we're going to use the equation that I've given you now. Here it's the same equation in the notes. Again, it's an empirical equation, and the head loss is a function of your approach velocity squared, the depth of your bed. It's inversely proportional to the sphericity, the porosity, and the diameter of your media. We need to check the effective size and the uniformity coefficient. The effective size is that D10, and the uniformity coefficient is D60 over D10. So what I've done here is I've plotted the data that we were provided as the sieve size. So this is millimeters. So this is looking back to here. That's this sieve size here versus the cumulative mass passing. And I've plotted that on log probability paper. So each one of these is a point. And what we need to calculate is this D10 right here. So this corresponds to my D10, and then the D60 is up here. So this is my D60. And the effective size is 0.3. My P60 is right here, is equal to 0.82. And this would give me an effective, uniformity coefficient of 0.82 divided by 0.3, and that is 2.73. This value should be between 1.3 to 1.8, and the Glum standards state that it should be less than or equal to 1.65. Basically, so it's more uniform. What do I do now? I'd have to go back to the company, the supplier of the sand, and say that I need a sand that meets this criteria. So for your design project, there is a company, Red Flint. They're located in Minnesota, I believe. Minnesota or Wisconsin, I forget which now. They have the type of information that we need available on their website. So what you'll be doing for further aspect of your mini design is you will be using the data available from Red Flint to choose a sand that will meet this criteria. We're going to move forward with this. This corresponds to the example in the textbook, but in reality and in your design project, you'll pick the sand, and you want a sand that meets these requirements. So the next thing we'll do is we want to reorganize the data. So what we're looking at is the percent retained between two sieve sizes. So if you look here, this 2.2 is 99.0 minus 96.8. So what we were given was the cumulative mass passing. And if we go back to this information here, we're looking at the percent retained in this fraction right here, in the sieve size 6 to 8. So that gives us this value right here. This 5.3 comes from, we'll look at the next, we'll look at 8 to 12. And that's 6.8 minus 91.5, and that's 5.3. So these are percent. We need to calculate the geometric mean of your particle size. So here, what you're looking at is the mesh size, 3.36 millimeters times 2.38. So this is the mesh sizes of the 6 and the 8 sieves. We'll multiply those and take the square root. That's the geometric mean. So my geometric mean diameter between the sieve size 6 and 8 is 2.8279. The geometric mean for between the 8 and the 12 is 2.38 times 1.68, and we take the square root of that, and that is 1.9996 millimeters. So that gives us the geometric mean. The next thing we want to do is to calculate the approach velocity. So we'll go back here. We're going to use this situation. We've decided that we're going to design the system with 4 filters at 80 square meters. So we'll use an approach velocity of 135 meters per day, but we need this in meters per second. So we'll divide 86,400 seconds per day, and that is 0.001563 meters per second. You're told that the shape factor or the sphericity is 0.82. The kinematic viscosity is 1.307 times 10 to the minus 6 meters squared per second at 10 degrees C. And then D is the geometric mean. I'm going to stop there. My advice between now and Friday is you try and calculate these values. And then what we'll do is we'll proceed through here, and then we'll calculate the head loss of the clean filter bed. So let's stop here. For the Reynolds number, what happened to the rest of the factors? This is the same Reynolds number that we used before. So I'm not sure the question. What factors?
Oh yeah, it only has VA on the top, so I was wondering what happened to like the shape factor.
So this is actually, the shape factor is actually included in here.
Oh,
So
okay.
get this value here. It's 0.82 times 1.996 times 10 to the minus 3 meters. We'll go over this on Friday. 1 times 1.56 times 10 to the minus 3 meters per second divided by the viscosity. So it's all included. It's included in this value here. So this is the, to get this value here, I'm substituting in this whole equation here. Does that make sense?
Yeah, thank you.
No problem. So we left off on Wednesday, where we're looking at designing a new water treatment plant. We've been given a design loading rate, and we've given the design flow rate for the plant, and we've been told some information about the client's preference in terms of the size, and this could be, it's likely dependent on the space availability. And the first thing you were asked to do is to estimate the clean filter head loss. So we've gone through quite a few calculations. We have gotten to the point where we have calculated the Reynolds number based on the geometric mean diameter of the particles for each size distribution. We've got the approach velocity that we've calculated and the viscosity for the temperature that we were told to use. So we've calculated R for the first set of data. Just make sure that we're good here. And this is this value right here. I'm sorry, this is this value right here. So we've used this diameter. And we can do this on an Excel spreadsheet, which is basically all of this data is from an Excel spreadsheet. So the next thing we want to do is calculate the coefficient of drag. So we will use the general form for the coefficient of drag. So we have the R values. So for this distribution here, we have that the coefficient of drag is equal to 24 divided by R plus 3 divided by the square root of R plus 0.34, and that's equal to 14.73. And we continue doing the same sets of calculations for each of these size. And the next thing we need is that summation term that's in our head loss equation. So this is this term right here, where we've multiplied CD times the fraction retained, so F is equal to the fraction retained, divided by D, our diameter. And we will continue to use the geometric mean diameter. Again, here we have a coefficient of drag now of 14.7264. The fraction retained is the percent divided by 100, divided by the diameter, but we need this in meters. So notice this is in millimeters, we need meters here. And that is 390.3. We could do the same here for this here, and this would simply be 10.79937 times 2.2 over 100, and we would divide that by the diameter, and that is equal to 84. So we continue to do all of those calculations, and then we will sum the values in this column. And we're using this equation here to calculate the head loss. And this is the head loss of the clean filter. So this is equal to 1.067, our approach velocity in meters per second, times the depth divided by the shape factor times G times the porosity to the fourth power times this summation, this value right here. And that is equal to 0.49. And your clean filter head loss should be less than 0.6 meters. So we are good there. Now, if that hadn't been the case, what would we do? Our only real options are to change the approach velocity and change the depth, or to pick a different sand so that we change the porosity. But as you can see, once we start operating the facility, changing the porosity is not an option. Changing the depth is not an option. The only thing we can change is our approach velocity, but that's dependent on demand. Now, once we've designed the filter, we need to calculate the backwash rate. The criteria for that is that we need to retain the finest sand grains. So if you remember, we have a depth of our filter. We have the gullet here. We need to fluidize this bed. So when we backwash, we expand the bed. So we have depth of the expanded bed. We need to make sure that we don't lose the finest grain sand grains. We want the water to flow into the trough, but we don't want the sand to flow into the trough. So we've got that criteria, and then the other criteria is that we need to fluidize the largest grains to release this particulate matter. Now, the problem with this whole approach that we've been using is we can't use Stokes' law because the flow regime is turbulent. Your targeted expansion rates are at least 37% for sand and 25% for anthracite. And the reason it's less for anthracite is because anthracite is less dense. Back many years ago, when in the East Lansing Rhodian Township plant, when they first put in anthracite within their sand filters, they didn't calculate the backwash rates properly, and they actually washed out much of their anthracite. So they ended up having to rebuild their filters. This is costly. They also had to reduce their backwash. The equation that we will use is that the depth of the backwash is equal to 1 minus the porosity, and this is of the fixed bed, times the depth of the fixed bed. So this is the during operation, times the summation of the filter media with expanded bed porosity. And we'll go through this calculation. The porosity of the expanded bed is a function of the backwash velocity and the terminal settling velocity of each of that particle grain size. And we'll use the Reynolds number. We'll include the shape factor in the Reynolds number. So let's go through the rest of these calculations. We again have the same set of data. So we have our grain size distribution, and we have the geometric means that we calculated previously. Figure 8-7 in your textbook is a graph that allows you to estimate a particle settling velocity dependent on particle diameter and specific gravity. So the particles of sand that we have a specific gravity of 2.65. This 2.6 is close enough, so we will use that. So what you'll simply do is you have a particular size. So for instance here, and we'll read across to calculate or to estimate the particle terminal settling velocity. So we can look at, we've got a diameter of 2.8. So that is over here. So it's 2.678. And this graph is kind of funky in terms of where this is 2.05 here. So this would be 2.08. And we read up and we read across. So that gives us an estimated value here for our terminal settling velocities. And don't worry so much about estimating these all that carefully because we're going to iterate on a solution. So this would be 0.28 here, for example. Okay. This next 0.28 here, this is 0.34. So this is our first estimate. And what I've done here is I've just tabulated that information here from the graph. So you can see for the particle size of 2.8 millimeters, I have a terminal settling velocity of 0.34. For 1.996, I have 0.28. So I go through and I count and I estimate, so these are estimated values from the graph. The next thing I'll do is I'll use that estimated terminal settling velocity to calculate the estimated R. So we've calculated the Reynolds number the same way as before. It is our shape factor times the geometric mean times the terminal settling velocity, so the estimated value, divided by the viscosity of 1.307 times 10 to the minus 6 meters squared per second. And that will give us an estimated R value. We then can use that estimated R value to calculate the coefficient of drag. So we're just substituting in here. So that is equal to 24 over 603 plus 3 divided by the square root of 603.2 plus 0.34. And we continue to do all those calculations, and that gives us the coefficient of drag for each of those particle fractions. We can then use the more general form of Stokes' law to calculate our terminal settling velocity. And notice we're using the same formulas that we talked about in sedimentation. And here, now we can calculate for this value here. We have 4 times 9.8 meters per second squared times the density of our particles times the diameter. So it's again your geometric mean, again in meters, divided by 3 times my coefficient of drag times the density of the water, and this whole thing to the square root. And that is this terminal settling velocity. And notice it's not much different from what we estimated from the graph. Now, we said that we need our backwash velocity to be less than the terminal settling velocity of the smallest particles, which means that our terminal settling velocity has to be less than 0.0107 meters per second. I'm sorry, backwash velocity has to be less than 0.0107 meters per second. What you will then do is iterate on a solution. So let's start, and we'll pick a backwash.
Could you scroll up just a little bit, just for a second?
Sure. So this is the backwash velocity of the smallest particles. And we want to make sure that the backwash velocity, okay, is less than that. When you're running these calculations, and if you go through the Excel spreadsheet, if you get negative values here, then your backwash velocity is too high and you'll need to reduce it. So the next thing you want to do is calculate the expanded bed porosity. And we want a expanded bed that's at least 37% greater than the fixed bed depth. So the equation we'll use here is that the depth of our expanded bed is 1 minus, same equation I gave before, 1 minus the porosity. This is the porosity of the fixed bed. And this is the depth of the fixed bed. This is the porosity of the expanded bed. And we calculate the porosity of the expanded bed using this equation right here. We need accurate values for R, so we'll use these calculated terminal settling velocities. So we're using the terminal settling velocities that we just calculated, and we'll calculate R as we've done before. So for instance, we've got 0.82 times 2.8279 times 10 to the minus 3 meters times our terminal settling velocity. So we're using the terminal settling velocity here in meters per second, and we'll divide that by the viscosity, and that is this value, it's 618. So what we need to do is we need to pick a bed wash velocity. And as I said, this has to be less than that 0.0107 meters per second, the terminal settling velocity of the smallest particles. What we will then do is calculate the bed porosity, the expanded bed porosity for each particle size. So this is simply 0.010 divided by 0.3487 times 0.2247, obviously an empirical equation, times 618.6544 to the 0.01. And that is this value right here. Okay. We do the same thing. If you get a negative value, so if you get a negative value in step 8, that means your backwash velocity is too high. Okay, so in this case, if any of these values are greater than 1, so if any of these are greater than 1, your backwash velocity is too high, and you need to reduce the backwash velocity. Okay. So for instance, if we had used a backwash velocity of 0.011, you would actually get values here greater than 1. You'd have negative values down here, and you'd reduce your backwash. So the next step is to calculate the fraction divided by 1 over your expanded bed porosity. So this is equal to 0.022 divided by 1 minus this expanded bed porosity, and that is equal to this value. and we will sum all of these values. Again, no negative values. If you have a negative value here, you reduce your backwash velocity. So this sum from this column is what we will use. And then finally, we will calculate the depth of the expanded bed. And that is equal to 1 minus 0.45 times the depth of our fixed bed times the summation value from the previous page. And that is equal to 0.7251 meters. And we have 0.7251 meters divided by my fixed bed depth, and that is equal to 1.45, or a 45%. So we're greater than the 35% recommended, and we're very close to the GLUM recommendation of 50%. We're not quite at that 50%, but we're close. And you can see how we could increase that backwash velocity a little bit, but we need to be very, very careful because it's calculations are very, very susceptible to a negative value and essentially washing out your fine sand. Now, each centimeter increase in water temperature means that we need to increase the backwash velocity to prevent reduction in the bed expansion. And that's as we increase temperature, we decrease the viscosity. So to counter that, as temperature increases, we need to increase backwash velocity. For groundwater, that's typically not an issue because your groundwater temperature is fairly constant. If you're treating surface water, especially if it is a near surface intake, your temperature will vary significantly. Just to give you, in Flint, when they were treating the Flint River water, the temperature varied over that roughly 18 months that they were treating from 2 degrees centigrade to 23 degrees. So they had a 21 degree centigrade change in temperature. And that temperature affects sedimentation, it affects the backwash, velocity calculations, etc. You want to design for the warmest water that can be expected, and that's in order to size your pumps. As long as we have variable speed, we can reduce the pumping rate. We can then reduce the pumping rate so that we don't wash out our fines during the colder temperatures. And as I mentioned above, we want 50% expansion. Now, if we were to increase this, if we increase our backwash velocity from 0.01 to 0.0101, we would get 50%. Sorry, this equals 36.4 meters per hour. And that would achieve 50% expansion. And our bed depth would be 0.749. So very small changes to go from 45% to 50%. Typically what you will do is you will add 0.15 meters height to the weir edge above the undisturbed media. So you're providing an additional depth. So once you calculate your depth of your expanded bed, we're going to add 0.15 meters to try and ensure that we don't wash out the sand. And just to do one last calculation, at the 0.01 meter per second, we have bed a filter that's 80 meters squared in surface area. And I'm going to convert to gallons, but just to give you a sense of when we're backwashing. At 0.01 meters per second may not seem like translate to a large volume of water. It is actually, we were pumping almost 13,000 gallons per minute to achieve that backwash rate here. And then just to give you a sense of how much water this corresponds to, that 0.5 cubic meters per second, if we calculate how much water we treat in gallons per day, that is 9.5 times 10 to the 6 gallons per day. If we have to backwash 3 times per day for 10 minutes each time, that corresponds to almost, well, just over 380,000 gallons per day. And then if we divide this by the amount of water that we produce times 100%, that is 4% of our entire flow that we produce per day goes to backwashing. So we want to minimize the number of times we backwash per day if we can, and the amount of time that we have to backwash, because that's using a significant amount of our produced water to backwash that filter. So all I've done here is just calculated, this was our flow rate that we started, and I calculated how many gallons per day that we produce, just to give you a sense. So we're talking about 10 million gallons per day that we would be producing, roughly. And then this is how much water we use every time we backwash. Or the flow rate when we backwash. So if we backwash for 10 minutes, 3 times a day, we're using roughly 380,000 gallons of water in that day. It's roughly 4% of our flow rate. So any questions about filtration? So what measures would you take to limit the amount? You want to make sure that you have efficient sedimentation. The poorer the efficiency of your sedimentation basins, the more turbidity you're loading onto your filters, and the more often you're going to backwash. So it's really making sure that your upstream processes are working properly so that you're not having to backwash as often. Other questions? Let's go back just to put this reminder slide back up here.